The bootstrap paradox is a fascinating thought experiment in time travel and causality. It involves a situation where an object or piece of information exists without ever being created. This creates a loop where the origin of the object or information cannot be traced back to any initial point in time. The basic concept: the bootstrap paradox occurs when an item, like a book, piece of technology, or a piece of knowledge, is sent back in time and becomes the catalyst for its own creation in the future. This creates a causal loop where the item or information exists, but there's no clear starting point for its existence. Example of the bootstrap paradox. One of the most famous examples of the bootstrap paradox is as follows. 1. A time traveler goes into the past and gives Shakespeare a copy of his works, his plays, sonnets, etc. 2. Shakespeare then copies these works down and publishes them as his own. 3. In the future, the time traveler finds these works, goes back in time, and gives them to Shakespeare again. Now, the paradox is, who is the true author of Shakespeare's works? The works exist, but they were never originally created by Shakespeare. He simply copied them from the future. In this case, the knowledge or work has no clear origin because it was passed back and forth through time, creating a loop. Why is it called bootstrap? The term bootstrap comes from the idea of pulling yourself up by your own bootstraps, which implies doing something impossible or self-sustaining. In the case of the paradox, the item or information pulls itself up from the future, creating its own existence in the past. Paradox explained. In the bootstrap paradox, the object or knowledge exists, but there's no original point where it was first created or originated. The loop of causality creates a situation where the object simply exists, but no one actually creates it. Significance. This paradox raises interesting questions about time travel, causality, and the nature of time itself. If time travel were possible, could we potentially cause objects or information to exist without an original creator? How would this affect our understanding of cause and effect? In short, the bootstrap paradox challenges our understanding of causality and time travel, presenting a scenario where objects or knowledge exist without an origin point, leading to a self-sustaining loop that defies logic. The grandfather paradox is a famous thought experiment in the context of time travel. It presents a logical contradiction that arises when a person travels back in time and changes something significant in the past, specifically an action that would prevent their own existence. Here's how the paradox works. The basic concept: 1. You travel back in time to a point when your grandfather was young. 2. You do something, for example, stop him from meeting your grandmother or accidentally harm him, that prevents him from ever having children. 3. As a result, your parent, who would not have been born, never comes into existence, and you are never born. 4. If you were never born, then you couldn't have traveled back in time to interfere with your grandfather's life in the first place. The paradox. The paradox creates a logical loop. If you were never born, you couldn't have traveled back in time, which means your grandfather's fate would be unchanged and you'd still be born. However, if you are born, it would allow you to go back in time and interfere again, creating a never-ending cycle. This leads to a contradiction where your existence both does and doesn't happen. The problem: The grandfather paradox challenges our understanding of causality and time travel. It raises questions like, can time travel really change the past without creating logical inconsistencies? Would actions in the past be able to erase or change the future in such a drastic way? Does time work in a way that would prevent such paradoxes from happening? Possible solutions or interpretations. 1. The many worlds. Interpretation. One possible solution is the idea of parallel universes or alternate timelines. According to this theory, if you traveled back and changed something in the past, you would create an entirely new timeline, a parallel universe where your grandfather never had children and you were never born. In this new universe, you wouldn't exist, but your original timeline still exists where you were born. 2. Self-consistency. Principle. Another idea is that the universe has built-in mechanisms to prevent paradoxes. This principle suggests that any action you take in the past, no matter what you try to change, would be constrained in a way that would prevent paradoxes. For example, if you tried to harm your grandfather, something might intervene to ensure that your grandfather's life unfolds in a way that preserves your existence. 3. Time travel is impossible. Some theories suggest that time travel to the past might be impossible in the first place. If this were true, the grandfather paradox wouldn't actually occur because traveling back in time would be prevented by the laws of physics. Conclusion. The grandfather paradox is a thought-provoking example that illustrates the potential contradictions and challenges of time travel. It questions how actions in the past could influence the future and whether time travel could be logically consistent or even possible. While it's a fascinating paradox to consider, it's also a reminder of how our understanding of time and causality is still evolving in both science and philosophy. The predestination paradox, also known as a causal loop, is a time travel paradox in which events that occur in the future cause actions to take place in the past, which then lead to the same events happening again in the future. This creates a loop where the past, present, and future are all connected in a circular chain of events. The basic concept: in a predestination paradox, a time traveler goes back in time and does something that ensures their own future happens exactly as it was supposed to. Essentially, their actions in the past are the very reason they travel back to the past in the first place, creating a self-sustaining loop of events. Example. Let's break down the paradox with an example. 1. A person from the future travels back in time and gives Shakespeare a copy of his plays. 2. Shakespeare then publishes those plays as his own. 3. The person in the future reads Shakespeare's works and is inspired to travel back in time to give Shakespeare the plays again, creating a loop where the works of Shakespeare are passed back and forth through time. In this case, the future action, the time traveler giving Shakespeare his works, is dependent on the past event, Shakespeare writing those same works, and vice versa. There's no original point of creation for the works of Shakespeare. They simply exist because they are passed back and forth through time. Why it's a paradox. The paradox occurs because there's no clear origin of the event or object. The actions of the time traveler in the past are what make their future actions possible. But without the past action happening, the future would not happen as it does. It's a self-sustaining loop with no beginning or end point. Key features of the predestination paradox: no free will. The paradox suggests that events are predestined or fated to happen in a certain way, with no room for change or deviation. Causal loop. Events from the future influence actions in the past, creating a loop that repeats itself. Closed timeline. The timeline is closed, meaning the same sequence of events happens over and over without any change or interference from outside factors. Possible solutions or interpretations. 1. Self-consistency principle. This principle suggests that events in the past would always unfold in a way that prevents contradictions. For example, if you tried to change something in the past, it would end up helping you fulfill the role you are destined to play. Any action you take in the past would be part of a plan that leads to the same future, preventing any paradox. 2. Multiple universes. Some theories suggest that actions in the past could create new parallel timelines or alternate universes. In this scenario, your actions in the past don't change the original timeline, but create a new one, leading to multiple possible realities. 3. Fixed timeline. Another theory is that the timeline is fixed and cannot be altered. Any attempts to change the past are already accounted for, meaning whatever you do is part of the grand plan, and nothing can prevent the future from unfolding exactly as it is supposed to. Conclusion. The predestination paradox challenges our ideas of free will and causality. It suggests that time could be a closed loop where the past and future influence each other in a way that doesn't allow for change. This paradox is often explored in science fiction, raising questions about fate, destiny, and the nature of time itself. The information paradox is a concept primarily discussed in the context of black holes and quantum mechanics. It arises when information about matter that falls into a black hole appears to be lost, which contradicts one of the fundamental principles of physics, that information cannot be destroyed. The problem: in classical physics, it was thought that once something entered a black hole, a region of space with extremely strong gravity, it would be lost to the universe forever. The event horizon of a black hole, the point beyond which nothing can escape, seemed to mark the point of no return, where all the information about the matter that fell in would be lost. However, according to quantum mechanics, information cannot be destroyed. This is known as the conservation of information, a principle that asserts that the complete information about a physical system should always be preserved, even if that information is hidden or encoded in a different form. The conflict between these two ideas, the loss of information in a black hole and the conservation of information, created the information paradox. The paradox. The information paradox arises because when matter, or information, falls into a black hole, the standard theory predicts that the information is lost, which contradicts the no-deletion principle of quantum mechanics. According to quantum theory, the complete state of a system at one point in time should be able to determine its state at any future point. However, if the information is lost inside the black hole, we wouldn't be able to reconstruct the system's original state, which would violate the laws of quantum mechanics. The Hawking radiation solution. One of the most famous attempts to resolve this paradox came from the physicist Stephen Hawking in the 1970s. He proposed that black holes can emit Hawking radiation, a form of radiation that causes black holes to slowly lose mass and eventually evaporate over time. According to Hawking's theory, The radiation emitted by black holes might contain information about the matter that fell in, potentially resolving the paradox. However, this solution raises its own issues and questions, such as how exactly the information is encoded in the radiation, and whether the information is completely recovered after the black hole evaporates. Potential solutions. 1. Holographic principle. One approach to solving the information paradox comes from the holographic principle, which suggests that all the information inside a volume of space can be encoded on the boundary of that space. This would mean that the information falling into a black hole might be stored on its event horizon, and as the black hole evaporates, the information could be recovered from this boundary. 2. Black hole. Firewall. Another hypothesis is the idea of a firewall at the event horizon of a black hole. According to this theory, the information may not actually enter the black hole, but instead could be destroyed at the event horizon by a firewall of intense radiation. However, this idea contradicts the principle of relativity, which says that an observer falling into a black hole should not experience anything unusual at the event horizon. 3. Information is preserved in the black hole. Some theories suggest that the information might be preserved in some form within the black hole, encoded in quantum states, but it is just difficult to access or observe. This might mean that the information is not lost, but rather hidden in a way that we do not yet fully understand. 4. Quantum entanglement and black hole. Complementarity. Another theory proposes that the information that falls into a black hole may be preserved in a quantum entangled state, a phenomenon where particles become linked in a way that the state of one can affect the state of the other, even across vast distances. This could lead to a situation where the information is not lost, but is encoded in the relationships between particles inside the black hole and the surrounding space. Conclusion. The information paradox is one of the most intriguing and unresolved issues in modern theoretical physics, and it challenges our understanding of black holes, quantum mechanics, and the nature of information itself. While there are several proposed solutions, there is no consensus in the scientific community on how exactly information behaves inside black holes. It remains a topic of active research and debate among physicists. The ontological paradox is a philosophical concept related to time travel and causality. It refers to a paradox in which an object or piece of information exists without an original creator, typically due to a causal loop. The term ontological comes from ontology, which is the branch of philosophy concerned with the nature of being, existence, and reality. The ontological paradox specifically involves the idea of existence without origin. The basic concept: in an ontological paradox, something exists because of itself, but there is no clear origin or point of creation. The object or piece of information comes into existence due to a causal loop, meaning it perpetuates itself across time, without any clear initial cause. This creates a situation where something simply exists without being created or originating from anywhere. Example of the ontological paradox. A classic example of the ontological paradox involves time travel and a causal loop. 1. Imagine a time traveler from the future who travels back in time and gives a writer a copy of their own book. 2. The writer, having received the book, publishes it. 3. The time traveler then reads the book and, inspired by it, goes back in time to give the writer the book again. In this case, the book exists because it was passed back in time by the future time traveler. But there is no clear origin for the book. The writer didn't create it, they received it from the future. Similarly, the time traveler wouldn't have been inspired to go back in time without reading the book. So the book exists without anyone truly creating it. This creates a causal loop. The book exists because of itself, with no initial point of creation. Why, it's a paradox. The paradox is ontological because it involves an existence without origin. In this case, the object, the book, exists because it was passed between the future and the past, but there is no first moment when the book was created or originated. It's as if the object exists without anyone actually creating it, creating an infinite loop where it simply exists without a cause. Philosophical implications. The ontological paradox raises deep questions about the nature of existence, causality, and time. It challenges our conventional understanding of how objects or information come into being, particularly in scenarios involving time travel and loops. Potential solutions or interpretations. 1. Self-creation. One solution might be to think of the object as self-created or self-sustained, where its existence is perpetuated through time, but there's no single moment of creation. 2. Multiverse theory. According to some interpretations of time travel, the actions of a time traveler might create an alternate timeline or parallel universe where the loop happens. But it doesn't affect the original timeline, meaning the object's origin could be traced to a different universe. 3. Closed timeline. Some theories suggest that the timeline is closed and self-consistent, meaning that the object or information is simply part of the universe's inherent structure without requiring an origin. Conclusion. The ontological paradox challenges our understanding of causality and existence, particularly in scenarios involving time travel or self-sustaining loops. It raises questions about how things come to exist without a clear origin and what it means for something to be if there's no initial cause. This paradox is an important concept in both philosophy and theoretical physics, as it pushes the boundaries of our understanding of time, existence, and reality. Polchinski's paradox is a thought experiment proposed by physicist Joseph Polchinski in 1990, which highlights a potential problem with time travel, particularly involving closed time-like curves, CTCs. CTCs are paths in spacetime that loop back on themselves, allowing time travelers to travel into the past. The paradox is meant to demonstrate a potential causal inconsistency in the concept of time travel and the effect it might have on the laws of physics. It's based on a situation involving a time traveler and a billiard ball. The setup of Polchinski's paradox. 1. Time travel and the closed time-like curve. Imagine a person travels back in time along a closed time-like curve, CTC, a path through spacetime that allows them to revisit the past. 2. The billiard ball. Let's say the time traveler, upon arriving in the past, throws a billiard ball at a specific point in time and space. 3. The paradox. The time traveler's action causes the billiard ball to hit something, and later, in the original timeline, the ball is sent back in time to the same person who throws it, essentially creating a loop. The ball appears in the past, but it's not clear where it came from. It's as if the ball exists without any origin, creating an ontological paradox, as the ball exists, but no one actually created it. 4. The core issue, The paradox arises from the causal loop, where the time traveler's action creates a chain of events that is self-consistent. The ball must be thrown to complete the loop, but it creates a scenario where the ball exists without any clear point of creation. In this case, the billiard ball would be both the cause and the effect of the same event, but its origin remains unclear. Why it's a paradox: causal consistency versus causal loop. The paradox highlights an apparent contradiction in the concept of time travel. How can an event, in this case, the creation of the ball, exist if it has no clear cause? The billiard ball essentially becomes a self-caused object, which seems to defy our understanding of causality. Something cannot exist without a cause or origin. Closed time-like curves, CTCs. In relativity, closed time-like curves theoretically allow for time loops, that is, traveling back in time. But the paradox suggests that such loops might create inconsistencies. The existence of the ball without origin becomes a violation of causal determinism, the principle that every event has a cause. Potential resolutions or ideas. 1. Self-consistency principle. One possible resolution is the principle of self-consistency, which states that events that involve time travel must be self-consistent. In this view, no paradox would occur because the actions of the time traveler would always work out in a way that avoids any contradictions. For example, the ball might not actually exist until it's thrown, thus resolving the paradox. 2. Multiverse theory. Another potential resolution involves the idea that time travel to the past could create an alternate timeline or parallel universe. In this case, the events of the time travel would happen in a new timeline where the ball exists, but the original timeline remains unaffected. This would avoid causal loops and paradoxes by positing that each time travel event creates a new branch of reality. 3. Quantum mechanics and non-locality. Some theories suggest that quantum mechanics might play a role in preventing paradoxes. For example, the behavior of quantum particles might inherently prevent certain paradoxes from occurring. Or perhaps the information related to such events could be encoded in a way that prevents the paradox. Conclusion. Polchinski's paradox is a thought experiment that challenges the consistency of closed time-like curves and time travel by showing how such systems could potentially lead to causal loops and paradoxes. The paradox highlights issues with the idea of objects or events being both the cause and effect of themselves. Though there are various potential resolutions to the paradox, it remains a valuable tool for discussing the limitations and problems that might arise with time travel, especially within the context of relativity and quantum mechanics. The causal loop paradox, also known as a causal loop, is a time travel paradox where an event or object in the future causes an event in the past that leads to the same future event, creating a loop of causality with no clear origin. In other words, the loop forms when an event or piece of information influences its own cause in the past, creating a closed cycle that repeats itself. How the causal loop paradox works. A causal loop typically involves time travel, where a person or object travels back in time, performs an action, and this action becomes the very reason the time traveler exists or the event occurs in the future. Here's an example of how the paradox can play out. Example of a causal loop paradox. 1. The time traveler's action. A person from the future travels back in time to a specific point in the past. 2. The influence on the past. The time traveler meets a famous author or a scientist and gives them a copy of their own book or scientific discoveries that the time traveler themselves will later learn in the future. 3. The repetition of the event. The author or scientist uses the information, writes the book, or develops the discovery, and it is published. This becomes the very book or discovery that inspired the time traveler to go back in time. 4. The loop. The time traveler reads the book in the future, gets inspired, and goes back to give it to the author again. Thus, the cycle repeats. The time traveler exists only because they received the knowledge from the future that they themselves had created. Why it's a paradox. The causal loop paradox creates a logical contradiction because the event or object that causes the time traveler to travel back in time has no clear origin. The information or event exists only because it's part of a loop, but no one truly created it. This raises the question, where did the original idea or object come from? In this case, the time traveler could never have been inspired to go back in time without the future knowledge, and the knowledge exists because of the time traveler, creating a closed cycle with no beginning or end. Key features of the causal loop paradox. 1. Circular causality. The key feature of a causal loop is circular causality, where an event in the future causes an event in the past, and the past event, in turn, ensures the future event happens, creating an endless loop. 2. No origin. The paradox highlights the problem of origin. If an event is caused by something in the future that has no initial cause, where does it come from? This leads to a situation where the event exists, but has no clear point of origin. 3. No free will. In a causal loop, the future is already determined by the past and the actions of the time traveler, meaning there is no room for free will or the possibility of altering the timeline. Philosophical and theoretical implications. The causal loop paradox challenges our understanding of time, causality, and free will. It suggests that time travel could potentially create a reality where events are predestined and unchangeable, which questions whether we can ever truly change the past or if the future is set in stone. Possible resolutions. 1. Self-consistency. Principle. One potential resolution to the causal loop is the self-consistency principle, proposed by physicist Igor Novikov. According to this principle, any action taken by a time traveler would have to be consistent with the timeline and not lead to contradictions. In the case of a causal loop, this would mean that the time traveler's actions are always part of the loop and cannot be altered in a way that would cause a paradox. 2. Multiverse theory. Another resolution could involve the multiverse theory, which suggests that time travel to the past could create an alternate timeline or parallel universe. In this case, the causal loop could exist in one timeline, but the original timeline might remain unaffected. Each action could lead to the creation of a new, parallel reality. 3. Fixed timeline. The idea of a fixed timeline is another way to resolve the paradox. In this view, once a time traveler goes back to the past, their actions are already part of the established timeline, meaning that whatever happens in the past is meant to be, and no real paradox occurs. Conclusion: the causal loop paradox raises interesting questions about the nature of time, causality, and the potential consequences of time travel. It presents a scenario where events and objects loop through time in a self-sustaining cycle, leading to a situation where the origin of the event is unclear. While there are several theoretical ways to resolve the paradox, it remains a fascinating area of discussion in both philosophy and physics, particularly in the context of time travel and the nature of reality. The double time loop paradox is an extension or variation of the causal loop paradox. While both involve closed time loops, the double time loop paradox adds a layer of complexity by introducing two separate loops that influence each other, creating a situation where two events or actions are causally interconnected, each affecting the other in a cyclical pattern. Basic concept. In the double time loop paradox, there are two distinct time loops that are intertwined. Each loop creates a chain of causality that depends on the other, and both loops are closed, meaning that the events in both loops are interdependent. This results in a situation where the past and the future are entangled in two cyclical causal chains, potentially leading to complex paradoxes and contradictions. Example of the double time loop paradox. 1. The first loop. Imagine a time traveler, let's call them Person A, who travels back in time. In the past, Person A influences an event that leads to the creation of an object, let's say a book or a scientific discovery. This object becomes the inspiration for the time traveler in the future to go back in time and influence the event again. The object exists in the future because of actions that take place in the past. 2. The second loop. Simultaneously, another person, Person B, from the future, who also travels back in time, introduces a piece of information or an event that interacts with Person A's actions in the past. This second loop intertwines with the first, causing both loops to depend on each other. For instance, Person B might directly influence Person A's motivation or actions in the past. 3. The interdependency. Now, both time travelers and their respective actions are causally dependent on each other. The first loop would not be possible without the second, and vice versa. Person A's future existence depends on the success of Person B's intervention in the past. And Person B's intervention is only possible because of the influence of Person A's actions. In other words, the events in the past, where the time travelers went, create a web of interrelated events in the future and past, with no clear starting point. Why it's a paradox. The double time loop paradox complicates the causal loop paradox because it introduces two interwoven causal loops that reinforce each other. Each loop depends on the other for its existence, but both are equally causal in nature. This creates a paradox of mutual dependence, where no clear origin exists for the events in either loop. Origin ambiguity. Just like in the causal loop paradox, the paradox is created because the events that occur have no origin. The two loops perpetuate each other's existence without any clear initial cause or creator, leading to a paradoxical situation where it's impossible to trace the original point of origin for either loop. Contradictions in causality. By having two loops, the paradox introduces additional complexity. The actions of one time traveler affect the other in ways that make it hard to understand the true cause of events. The loops cannot exist without each other, but they have no starting point, leading to logical contradictions in causality. Key features of the double time loop. Paradox. 1. Two interwoven loops. Unlike the causal loop paradox, where one loop exists in isolation, the double time loop involves two loops that are interdependent. 2. No clear origin. As with other time travel paradoxes, the double time loop creates a situation where there is no clear origin or cause for the events, as the loops are perpetuated by each other. 3. Complex causality. The paradox highlights the problem of complex causality, where two separate actions in time from two different people interact with each other to create a cyclical and closed loop. Possible resolutions or ideas. 1. Self-consistency principle. The self-consistency principle suggests that time travel is self-consistent, meaning the events in the loop must always work out in a way that avoids contradictions. This might mean that the actions of person A and person B will always follow a path that ensures no paradox occurs, even though the two loops are interwoven. 2. Multiverse or alternate timelines. According to the multiverse theory, the events of the double time loop might occur in parallel universes. The actions of each time traveler could create alternate timelines or branches of reality, so that the paradox does not affect the original timeline. 3. Fixed timeline. Some theories propose that timelines are fixed and unchangeable. In this view, the actions of the time travelers are part of a predetermined and self-sustaining timeline that prevents any paradoxes or contradictions from arising. 4. Quantum mechanics and non-locality. Quantum theories might provide a solution where the actions of the time travelers are governed by quantum probabilities rather than deterministic causality. This would mean that the paradox might be avoided by quantum uncertainty or hidden variables that prevent contradictions from occurring. Conclusion. The double time loop paradox adds complexity to the idea of time travel by involving two interdependent causal loops. Like other time travel paradoxes, it challenges our understanding of causality, origin, and time. The paradox illustrates the potential complications of time travel scenarios, where events can become entangled in closed loops that perpetuate themselves with no clear starting point. While various theories could offer solutions, the double time loop paradox remains a fascinating thought experiment that raises important questions about the nature of time and reality. The observer's paradox refers to a situation in physics and philosophy where the act of observation itself impacts the outcome or behavior of a system being observed. This paradox is most famously associated with quantum mechanics, particularly with the concept of wave function collapse. The paradox raises questions about the nature of reality, the role of observation in determining outcomes, and whether or not the act of measurement influences the system being measured. In the context of quantum mechanics, in quantum mechanics, the observer's paradox is related to the phenomenon known as wave-particle duality. In certain experiments, like the famous double-slit experiment, particles such as electrons or photons can behave both as waves and particles, depending on whether they are being observed. Without observation, when not observed, particles act as waves, exhibiting characteristics of superposition, existing in multiple states at once. With observation, when a particle is measured or observed, it collapses into a specific state, that is, behaves like a particle. The observation forces the system to choose a definite outcome from the possible probabilities. The paradox here is, how can an observer, by simply measuring or observing, affect the outcome of an experiment? The very act of observation seems to change the behavior of the particles, raising questions about the relationship between reality and observation. Double-slit experiment. One of the best known examples of the observer's paradox comes from the double slit experiment. 1. When no observation is made, particles, like electrons or photons, pass through two slits simultaneously and interfere with themselves, creating an interference pattern on a screen behind the slits, similar to how waves behave. 2. However, when observed with a detector at the slits, the particles act like discrete particles and the interference pattern disappears. Instead, they behave like particles and create two distinct bands on the screen. This experiment seems to suggest that the act of observation changes the way the particles behave. This has led to deep philosophical questions about the role of the observer in determining the state of reality. The paradox. The paradox is that the act of measurement or observation appears to determine the state of a system, collapsing it from a range of possibilities to one definite outcome. This raises the question: does reality exist independently of observation, or is the observer necessary to bring it into existence? In other words, does the particle choose a specific state only when it is observed? Is reality somehow incomplete or undefined until it is observed? Possible explanations or resolutions. 1. Copenhagen. Interpretation. This is one of the most popular interpretations of quantum mechanics, proposed by Niels Bohr and Werner Heisenberg. It suggests that the wave function, which represents all possible states of a system, collapses into a single state when observed. In this interpretation, observation is a key factor in determining reality at the quantum level. 2. Many worlds interpretation. In contrast, the many worlds interpretation of quantum mechanics posits that all possible outcomes of a quantum event actually occur, but in different parallel universes. In this view, the observer does not collapse the wave function, but simply becomes entangled with the outcome of the measurement in one of the parallel worlds. 3. Quantum decoherence. Another theory, quantum decoherence, suggests that the interaction of quantum systems with their environment, such as a measuring device, causes the system to lose its quantum coherence and behave classically, eliminating the need for an observer to collapse the wave function. 4. The role of consciousness. Some interpretations, like consciousness causes collapse, suggest that consciousness itself plays a role in collapsing the wave function. In this view, the observer's awareness of a quantum state is what forces it to settle into a definite state, though this is highly debated and speculative. Broader implications of the observer's paradox. Reality and perception. The observer's paradox forces us to confront questions about the nature of reality itself. Does reality exist objectively, independent of our observation of it, or is it fundamentally tied to how we perceive it? Philosophy of science. The paradox also touches on deep philosophical issues about measurement, knowledge, and the limits of scientific observation. If the observer influences the system, can we ever truly understand a system independent of our influence on it? The quantum suicide paradox is a thought experiment related to the many worlds interpretation of quantum mechanics. It is an extension of the Schrödinger's cat thought experiment and explores the implications of quantum mechanics on life, death, and consciousness, especially in terms of the observer effect and parallel universes. The setup of the quantum suicide paradox. The paradox centers on an experiment that involves a person and a device that determines whether they live or die based on a quantum event. Here's a simplified version of the experiment. 1. The device. Imagine a device connected to a quantum event, such as the spin of a radioactive atom. The quantum event is probabilistic. It has a 50% chance of causing a lethal event, for example, a gun firing, and a 50% chance of not causing harm. 2. The setup. The person is placed in a machine where, based on the quantum outcome, they either survive or die. The quantum event happens, and the result determines their fate. If the quantum event goes one way, they die, and if it goes the other, they survive. 3. The many worlds interpretation. According to the many worlds interpretation, MWI, of quantum mechanics, all possible outcomes of a quantum event occur, but each in a separate, parallel universe. In the case of the quantum suicide experiment, in one branch of the universe, the person dies. In another branch, the person survives. The idea is that the person may never experience their own death, because in every universe where they die, there is another universe where they survive. From the perspective of the person, they would always find themselves in a universe where they survive, even though in other parallel universes they may be dead. The paradox. The paradox arises from the idea that the person undergoing the quantum suicide experiment will never observe their own death due to the nature of the many worlds interpretation. Every time the quantum event occurs, the person will always survive in one branch of the multiverse, even though there are other branches where they die. In essence, the person's subjective experience will always be one where they survive, no matter how many times the experiment is repeated. Implications and interpretation. 1. Subjective experience of survival. According to the thought experiment, the person's consciousness would always continue in the universe where they survive. The paradox raises the question: does the experience of survival imply that the observer's consciousness chooses or follows the branch of reality where they remain alive, even though death occurs in other branches of the multiverse? 2. Role of consciousness. The quantum suicide paradox seems to challenge the idea that death can be an objective event for the observer. Instead, it suggests that subjective experience could be tied to the branch of reality where the observer continues to exist. It also implies that consciousness itself might be intrinsically linked to the experiences that occur in these separate universes. 3. Multiverse and the continuation of consciousness. If we accept the many worlds interpretation, the paradox suggests that there are no objective deaths for the observer, as their subjective experience always follows the surviving branch. This raises questions about how consciousness interacts with the universe. Does the observer's consciousness split with the universe? And does this imply some form of immortality in the context of parallel worlds? 4. Ethical considerations. The experiment is deeply philosophical and involves ethical concerns, as it imagines a scenario where a person's life is determined by quantum mechanics in a potentially dangerous way. The thought experiment doesn't suggest we should perform such an experiment, but raises serious questions about the nature of life, death, and consciousness in a quantum universe. Possible resolutions or critiques. 1. Questioning the validity of the experiment. One resolution to the paradox is to question whether the thought experiment is even feasible in the first place. Since the many worlds interpretation is just one possible interpretation of quantum mechanics, it's possible that other interpretations, such as the Copenhagen interpretation, would not allow for the idea of multiple universes where the person survives. 2. Physical and ethical limitations. Beyond the philosophical implications, performing such an experiment would raise serious ethical and physical concerns. Quantum suicide experiments are strictly theoretical and would never be conducted in reality. 3. The nature of consciousness. The paradox also touches on unresolved questions about the nature of consciousness. The idea that an observer's consciousness can follow the surviving branch in the many worlds model remains highly speculative and is a topic of philosophical debate. The mechanism by which consciousness would choose a branch of reality is not clear and remains a speculative concept in the realm of thought experiments. Conclusion. The quantum suicide paradox is a fascinating thought experiment that challenges our understanding of consciousness, life, death, and the many worlds interpretation of quantum mechanics. It suggests that, in a multiverse, an observer may never experience their own death because they would always find themselves in a universe where they survive. While it raises intriguing philosophical questions about the nature of reality and our perception of existence, it is ultimately a theoretical paradox that doesn't have a clear empirical resolution, and its implications for real-world quantum mechanics remain speculative. The Fermi paradox, in its classic form, questions why, given the vast number of potentially habitable planets in the galaxy and the immense age of the universe, we have not yet encountered any evidence of extraterrestrial civilizations. It highlights the contradiction between the high probability of intelligent life elsewhere and the apparent absence of contact. Now, if we consider the time travel version of the Fermi paradox, we can add another layer to the mystery by incorporating the idea that extraterrestrial civilizations may have already visited Earth, or may be able to, through time travel. This version suggests several possibilities. 1. Time travel and the limitations of observation, temporal blindness. Perhaps extraterrestrial civilizations are able to travel through time, but do so in a manner that we cannot perceive. They could be visiting in moments of time that we are simply unable to detect. Perhaps they exist in parallel time streams, or they manipulate time in ways that are invisible to us. Nonlinear time. If time is nonlinear, as some theories in physics suggest, then beings could already be here in the future or the past, but their presence is not within our narrow window of linear time. We might be unable to see them because we are stuck in a present that doesn't align with their temporal travels. 2. The zoo hypothesis and time travel. The temporal zoo. One version of the zoo hypothesis suggests that extraterrestrial civilizations are deliberately avoiding contact with us to let us evolve naturally without interference. The time travel version could propose that these civilizations have visited or are observing us at various stages in our development, but have done so from the future, where they have mastered time manipulation and can choose when and how to interact without revealing themselves. The temporal prime directive. What if there's a temporal equivalent of the prime directive from Star Trek, where advanced civilizations refrain from altering the past or interfering with less advanced ones to preserve the timeline? This idea would mean extraterrestrial civilizations are aware of humanity, but are bound by some temporal law not to make contact. 3. The temporal filter time travel as a filter. It's possible that civilizations reach a point where they can harness time travel, but choose to exit the linear timeline altogether, or they disappear into different time periods. The Fermi paradox could be a result of civilizations not existing in our time because they no longer adhere to the traditional flow of time. They may exist in future periods or have ascended into higher forms of existence beyond space-time. Temporal isolation. Another hypothesis is that as civilizations advance technologically, they become aware of the dangers of temporal paradoxes or self-destruction. Therefore, they deliberately choose to travel in such a way that they avoid direct interaction with other civilizations, possibly secluding themselves in different times. 4. Temporal observation past encounters. Could we have been visited by extraterrestrial civilizations, but their visitations were so long ago that no direct evidence remains? They may have visited in the distant past, and any evidence of their presence has been lost to time, whether through natural degradation or deliberate efforts to leave no trace. Futuristic observations of us. What if extraterrestrials are observing humanity, but from the future, where they have already solved the paradox of time travel? They could be waiting to make contact at a specific moment in time or gathering data about us as part of their own historical research. 5. Temporal anomalies and the search for evidence time travel paradoxes. The fact that we don't observe signs of extraterrestrial civilization may be a result of the paradoxes created by time travel itself. Extraterrestrials who visited Earth in the past may have inadvertently altered their own timelines or created paradoxes that prevent us from encountering them in the present. The universe could have some sort of temporal self-correction mechanism that erases evidence of such interactions to prevent catastrophic consequences. Evidence manipulation. The absence of extraterrestrial evidence might be due to some civilizations altering the timeline to remove any traces of their existence. Perhaps they travel back to key moments in history and remove artifacts or evidence that would indicate their presence, ensuring that the timeline remains undisturbed. In summary, the time travel version of the Fermi paradox asks whether extraterrestrial civilizations might be actively engaging with our timeline or have already done so in ways that are undetectable. Whether through temporal isolation, observation, or unseen intervention, the paradox deepens when time itself is a factor, raising the question of whether the real mystery is not that we haven't encountered aliens, but that they are already here. Schrödinger's time traveler paradox is a thought experiment that combines the concepts of Schrödinger's cat from quantum mechanics and the paradoxes of time travel. The basic idea is to apply quantum superposition, where an object exists in multiple states at once, to a time traveler who might alter the past, creating a situation where both outcomes, the time traveler successfully altering the past and the time traveler not doing so, exist simultaneously in an uncertain state. Here's a breakdown of the paradox. 1. The quantum superposition and the time traveler. In Schrödinger's famous experiment, a cat inside a box can be both alive and dead at the same time until the box is opened and the state is observed. This is a quantum phenomenon where the cat is in a superposition of states, and only upon observation does it collapse into one definitive state, alive or dead. Now imagine a time traveler who goes back in time and attempts to change a specific event, like preventing a disaster or killing an ancestor. According to time travel paradoxes, such an action would create a self-consistent loop or paradox, depending on the model of time travel. But if we apply quantum mechanics, the time traveler's actions are also in a superposition of both outcomes. They may either succeed in changing the past or fail. This situation exists in an uncertain, probabilistic state until the timeline collapses into a single outcome when observed. 2. The paradox in action scenario. 1. The time traveler alters the past. The time traveler goes back in time and successfully changes something. For example, they prevent an event that leads to their own birth. If they succeed, then the time traveler would never have existed in the first place. The paradox here is that the time traveler's existence becomes impossible, creating a logical inconsistency. If they never existed, how could they have traveled back in time to prevent their own birth? Scenario 2. The time traveler fails to alter the past. Alternatively, the time traveler goes back, but their actions have no effect on the course of history. This leads to a self-consistent timeline where the time traveler exists. The event happens as it originally did, and the time traveler is able to return to the future. However, in this scenario, the time traveler's journey back in time seems pointless, as they didn't change anything. 3. Superposition of possible outcomes. In Schrödinger's time traveler paradox, before the time traveler's actions are observed, whether by them or the timeline, the outcome is in a superposition of states. Both possibilities, the traveler succeeding or failing to alter history, exist at the same time. Just as the cat in Schrödinger's box is both alive and dead until observed, the time traveler's actions are both successful and unsuccessful until the timeline collapses into one version of events. 4. The observer and the collapse of the timeline. The timeline might be analogous to the state of the cat. Until the timeline is observed, either by the time traveler themselves or by a third-party observer, perhaps the universe or reality, the event remains in a superposition, meaning that the past can be both changed and not changed simultaneously. The timeline would collapse to a consistent version once the time traveler's actions are settled and the paradox resolved, whether that's a successful alteration or the failure to change the past. 5. Implications and speculation. This paradox introduces a few interesting possibilities and questions. Quantum time travel. What if time travel involves quantum mechanics at a fundamental level? Perhaps traveling through time involves entering a quantum superposition of potential timelines, with the observer, the time traveler, collapsing the timeline upon their arrival or action. Quantum time travel. What if time travel involves quantum mechanics at a fundamental level? Perhaps traveling through time involves entering a quantum superposition of potential timelines, with the observer, the time traveler, collapsing the timeline upon their arrival or action. Consistency of the timeline. In some models of time travel, the timeline is self-consistent. The universe prevents paradoxes. In this case, the time traveler might be unable to alter the past because the timeline automatically adjusts to prevent any inconsistencies, much like the concept of the many worlds interpretation of quantum mechanics, where every action creates a branching timeline. Causal loops and entanglement. If we apply quantum entanglement, it's possible that the time traveler's actions are already woven into the fabric of history. meaning the superposition of the timeline includes the time traveler's eventual actions, even before they travel back. Perhaps the paradox is just a manifestation of quantum entanglement over time. 6. Possible resolutions. Some theories that might help resolve this paradox include the many worlds interpretation, MWI. This suggests that all possible outcomes occur, but in different branches of the universe. So, if the time traveler changes the past, the timeline splits into two branches, one where the past is altered and one where it isn't. Both possibilities coexist in parallel realities. Novikov self-consistency principle. This principle posits that any action a time traveler takes is part of history and, therefore, must be self-consistent. For instance, the time traveler may try to change the past, but due to some unknown mechanism, they cannot change anything significant. Perhaps the universe actively prevents paradoxes. Time as a fixed dimension. Another possibility is that time is fixed in a way we don't fully understand. In this view, the concept of a superposition of events might not apply to time travel, because the timeline would already be set, and the time traveler would always be part of it. Conclusion. Schrödinger's time traveler paradox combines quantum mechanics with the classic problems of time travel, where a time traveler is both successful and unsuccessful in their attempts to change the past until the timeline is observed. It raises fascinating questions about the nature of time, reality, and observation, and plays on the idea that the universe may have built-in mechanisms, either quantum or self-consistent, that prevent paradoxes or force reality to resolve itself in a way that preserves the timeline. The reverse causality paradox, also known as backward causality or causal reversal, explores the idea that effects can precede their causes, effectively flipping the traditional flow of time where causes come before effects. This paradox can lead to various contradictions and logical conundrums that challenge our understanding of time and causality. 1. Basic concept of reverse causality. In classical physics and our everyday experience, causality follows a linear order: cause, effect. For example, if you drop a glass, the effect is the glass breaking due to the cause of it hitting the ground. In reverse causality, the effect would occur before the cause. This means the glass would break before it hits the ground, which would, of course, create a paradox, because how can an event occur before its cause? 2. The paradox. The reverse causality paradox typically arises when an event occurs before its cause, which undermines the principle of causality. Let's break down a potential scenario. Example 1. Time traveler's influence. Imagine a time traveler who travels to the past and causes an event that directly leads to their own creation. They arrive in the past and set into motion actions that lead to their own birth. This action, the effect, happens before the event, the cause. The time traveler's birth happens because of their intervention in the past. But if they hadn't been born, they wouldn't have been able to go back in time to create the event in the first place. The paradox here is, how could the time traveler exist to create their own birth if they weren't born in the first place? Example 2. The killing the grandfather paradox. This is a variant of the grandfather paradox in reverse causality. A time traveler goes back and prevents their grandfather from meeting their grandmother, which means the time traveler is never born. If the time traveler is never born, they cannot go back in time to prevent the meeting in the first place, creating a loop of contradictions. In reverse causality, the effect, the non-existence of the time traveler, precedes the cause, the time traveler's intervention. Example 3. Information paradox. In another scenario, a message from the future arrives in the past, giving a person information that leads them to take an action. This action causes the event that results in the message being sent in the first place. The person wouldn't have known to act unless they had already received the message, creating a situation where the message, effect, precedes the action, cause. 3. Problems with reverse causality creates several challenges to the traditional understanding of time and logic. Logical contradictions. Events cannot logically happen before their causes. If the cause is dependent on the effect, this creates a causal loop, which is logically incoherent. Temporal paradoxes. In reverse causality, it becomes difficult to pinpoint a single moment in time when the cause and effect relationship actually begins. In the classic case of time travel, for example, the time traveler's actions are tied to events both in the future and past, leading to the question, which is the true cause? Violation of entropy. In thermodynamics, entropy is a measure of disorder, and it tends to increase over time. Reverse causality would imply a decrease in entropy, a backward flow of time, which contradicts our understanding of how energy and information naturally evolve. 4. Possible resolutions. Though the reverse causality paradox creates logical inconsistencies, several potential resolutions or theoretical frameworks have been proposed in an attempt to make sense of these paradoxes. A. Multiverse theory, many worlds interpretation. One possible resolution to reverse causality is the idea of parallel universes, or the many worlds interpretation. In this theory, every time a time traveler alters the past, they don't alter their own timeline. Instead, they create a new parallel timeline. So, in the case of the grandfather paradox, the timeline where the time traveler is born and goes back in time exists in one universe, and the timeline where the grandfather is prevented from meeting the grandmother exists in another. This way, no paradoxes arise because the effect and cause happen in different branches of reality. Consistency of time. Novikov self-consistency principle. The Novikov self-consistency principle suggests that time travel is self-consistent, meaning that any actions taken by a time traveler must not lead to contradictions or paradoxes. If a time traveler goes back in time, they are somehow compelled to act in a way that ensures the timeline remains consistent and paradox-free. In the reverse causality case, this could mean that even if the traveler tries to cause an effect before the cause, the universe will prevent them from doing so in ways that preserve consistency, perhaps forcing events to occur in a way that ultimately doesn't create a paradox. See block universe theory, eternalism. In the block universe theory, time is viewed as a dimension similar to space, where past, present, and future events all coexist. In this view, the entire history of the universe is fixed and unchangeable, and all events, whether in the past, present, or future, are set in stone. Reverse causality would not create a paradox, because all events are already part of the block universe, and there's no flow of time that needs to be logically consistent. Events might seem reversed, but in this framework, time travel could be seen as merely shifting from one part of the timeline to another without altering its inherent structure. D. Temporal non-interference. Another possible explanation is that the universe, or laws of physics, might inherently forbid actions that would lead to reverse causality. Perhaps the structure of reality is such that, although time travel might be theoretically possible, events will always correct themselves in such a way that the flow of causality remains intact. Even if a time traveler goes back in time, they might only be able to influence events in ways that do not create paradoxes. 5. Conclusion. The reverse causality paradox challenges our fundamental understanding of time and causality by suggesting that an effect can precede its cause, creating complex logical and temporal inconsistencies. While this paradox remains unresolved in many theoretical frameworks, it provides a fascinating glimpse into the potential consequences of time travel and the nature of causality in a universe that might not be as linear and predictable as we think. Solutions like the multiverse, Novikov self-consistency principle, and block universe theory provide different ways of resolving or sidestepping the paradox, but the implications for time travel and our understanding of reality remain profound and intriguing. The Novikov self-consistency principle is a theoretical concept in the study of time travel, proposed by physicist Igor Novikov in the 1980s. It is a hypothesis designed to resolve paradoxes that arise from time travel by asserting that the laws of physics prevent any action that could cause a contradiction or paradox in the timeline. The principle suggests that if time travel is possible, the timeline must remain self-consistent, meaning that events, actions, and outcomes in the past must always conform to the laws of causality and avoid creating logical inconsistencies. 1. Key idea of the principle. The core idea behind the Novikov self-consistency principle is that any event that occurs in the past as a result of time travel must be consistent with the existing timeline. In other words, if a time traveler goes back to the past and attempts to change something, the timeline will prevent any change that would create a paradox. For example, if a time traveler goes back and tries to prevent their own birth, they will be guided in such a way that their actions still lead to their eventual birth, or they would be unable to alter events significantly enough to prevent their existence. 2. How it works. The Novikov self-consistency principle proposes that while time travel might allow someone to travel to the past, their actions are constrained by the need to preserve the integrity of the timeline. Essentially, any action a time traveler takes has already been factored into the historical timeline, meaning it can't cause an event to unfold in a way that would lead to a paradox. This principle ensures that time travel does not lead to logical inconsistencies like the famous grandfather paradox. Example, the grandfather paradox. In the classic grandfather paradox, a time traveler goes back in time and kills their grandfather before the time traveler's parent is conceived, thereby preventing the time traveler from ever being born. According to the Novikov self-consistency principle, something would occur to prevent the grandfather from being killed, or the time traveler would be unable to go back in time to begin with. Essentially, the universe would prevent the time traveler from creating a paradox. For instance, the time traveler might be prevented from carrying out the action, or they might inadvertently cause the grandfather's death in a way that doesn't negate their own existence. 3. Implications and examples. A. Preventing paradoxes. The principle suggests that even if time travel to the past is possible, there is a fundamental, self-correcting mechanism that avoids contradictions. This means that no matter what a time traveler does, their actions will not lead to situations that create paradoxes, because the timeline simply won't allow it. If a time traveler goes back and tries to stop a crucial event, the events will conspire to ensure that the timeline remains consistent. If the time traveler tries to prevent their own birth, the universe will prevent them from succeeding in a way that ensures their existence remains intact. Fixed history. The Novikov self-consistency principle suggests a view of time where history is fixed and unalterable. Events have already occurred in a self-consistent way, and any travel back in time must conform to that established history. In this view, the concept of free will or altering the past is an illusion. The timeline will always correct itself so that no contradiction arises. 4. Example of consistent time travel. Imagine a time traveler who goes back in time to prevent an important historical event. According to the Novikov principle, their attempt to prevent the event would fail, not because of some external force, but because the history of the timeline has already incorporated the event in a consistent way. The traveler might try to stop the event, but in the process, they may inadvertently cause it to happen or create circumstances that ensure it unfolds as it originally did. For instance, a time traveler goes back in time to stop a scientist from discovering a groundbreaking formula. The time traveler might attempt to destroy all the scientist's notes, but in doing so, they accidentally help the scientist remember key aspects of the formula, leading to the discovery being made in an unexpected way. This type of resolution ensures that the timeline remains self-consistent, meaning events unfold without causing paradoxes, regardless of the time traveler's attempts to interfere. 5. Relationship with the many worlds interpretation. While the Novikov self-consistency principle suggests that events in the past must remain fixed and consistent, it is distinct from the many worlds interpretation of quantum mechanics, which proposes that every possible outcome of an event, including the time traveler's actions, results in the creation of a new parallel universe or timeline. In the many worlds interpretation, time travel could lead to the creation of multiple parallel timelines, where changes in one timeline would create a branching reality. The Novikov principle, on the other hand, suggests that the universe will always enforce consistency in the original timeline, meaning no paradoxes or contradictions can arise in a single timeline. 6. Challenges and criticism. While the Novikov self-consistency principle offers a solution to time travel paradoxes, it raises some challenging questions. Why would the universe correct itself? The principle doesn't explain why or how the universe enforces this self-consistency. It simply asserts that it does. Free will and determinism. The principle leads to the idea that events are deterministic and fixed. If time travel is possible, it suggests that free will might be an illusion, as actions in the past must be consistent with a timeline that already exists. 7. Conclusion. The Novikov self-consistency principle offers a fascinating resolution to time travel paradoxes by asserting that the timeline remains self-consistent and paradox-free. It proposes that, although time travel to the past may be possible, the universe will always prevent any actions that would lead to contradictions or logical inconsistencies. This principle offers a way to avoid the paradoxes like the grandfather paradox, but it also raises deeper philosophical questions about the nature of free will, determinism, and the structure of time itself. The Killing Hitler paradox is a variant of the classic grandfather paradox in time travel discussions, specifically centered around the idea of going back in time and preventing a historical figure, like Adolf Hitler, from rising to power or being born. The paradox explores the implications of changing a significant event in history and the potential for creating logical contradictions. Here's a breakdown of the scenario and the issues it raises. 1. The paradox scenario. Imagine you, as a time traveler, go back in time with the goal of killing Adolf Hitler before he becomes a significant political figure. If you succeed, this would presumably prevent World War II and possibly alter the course of history in profound ways. However, this leads to a key issue. If Hitler never comes to power, then World War II might not happen, and the historical chain of events that led to your birth and to you having the desire to travel back in time might not unfold in the same way. If World War II never happens, then you may not have the motivation to go back in time to stop Hitler's rise to power, because the events leading to your decision and ability to time travel would not occur in a world where Hitler was never in power. This creates a causal loop, where the cause of your time travel, the motivation to stop Hitler, is tied to the very event, the rise of Hitler, that you are trying to prevent. If you prevent that event, you may no longer exist in the future, thus preventing you from going back in time to kill Hitler in the first place. 2. Causal loop and self-contradiction. The paradox essentially revolves around the self-contradiction created by trying to alter an event in the past that is directly tied to your own existence. If you kill Hitler and prevent World War II, your reasons for going back in time to stop the rise of Hitler would be negated, as World War II wouldn't happen, and the political conditions for your time travel would disappear. Therefore, you would have no reason or opportunity to go back in time to kill Hitler. This leads to an apparent logical paradox, because if you never travel back in time to kill Hitler, then the original history with Hitler in power and World War II could continue, and you'd have the motivation to go back again. The timeline becomes inconsistent. 3. Possible resolutions. There are a few potential ways to resolve or avoid this paradox, depending on the framework of time travel you adopt. A. Novikov self-consistency principle. Under this principle, the universe would prevent you from changing history in a way that creates a paradox. If you attempted to kill Hitler, something would intervene to prevent you from succeeding, because the timeline must remain self-consistent. Perhaps you'd fail to kill Hitler, or your actions would result in a different but equally significant historical event, such as Hitler's downfall happening through another means. In this way, the timeline remains consistent, and the paradox is avoided. Many worlds interpretation, parallel universes. In the many worlds interpretation of quantum mechanics, every possible outcome of a decision or event leads to the creation of a separate, parallel universe. So, if you go back in time and kill Hitler, it could create a branching timeline where a different history unfolds, without Hitler, without World War II. But your original timeline still exists in parallel, with its own course of events, including your decision to go back in time and kill Hitler. In this case, the paradox is avoided because your actions result in the creation of a new universe, not a contradiction within the original one. See Determinism and the Block Universe Theory. In some interpretations of time travel, particularly the block universe theory or eternalism, time is seen as fixed and unchanging. All events, past, present, and future, are already laid out in a 4D block of space-time. In this view, the future is just as immutable as the past, meaning that you cannot change history. No matter how hard you try, events like Hitler's rise to power would be part of the block universe. And even if you attempt to kill him, circumstances would align in such a way that his rise to power would still happen, possibly through different means. This would avoid a paradox because the past, present, and future are set, and changing one event would be impossible. D. Timeline stability and unchangeable events. Another possible resolution is that there might be certain key unchangeable events in history, moments that are critical to the development of human civilization and are protected from alteration by some unknown law or mechanism in the universe. In this view, even if you went back to kill Hitler, your efforts would be futile or thwarted in ways that still result in history unfolding similarly to how it originally did. This would preserve the timeline stability while also preserving your ability to travel back in time. 4. Moral and ethical considerations. While the killing Hitler paradox is a fascinating thought experiment, it also raises important moral and ethical questions. Many people argue that time travel to stop horrific events like the rise of Hitler would be desirable in order to prevent immense suffering. However, if we acknowledge that time travel is potentially fraught with paradoxes and unintended consequences, we must also consider the broader implications of altering the past. Even with the best of intentions, could our attempts to improve history lead to unforeseen negative outcomes? 5. The grandfather paradox versus killing Hitler. Paradox, the grandfather paradox, where you prevent your own existence by interfering in the past, is often compared to the killing Hitler paradox. Both involve trying to alter events in such a way that creates a causal contradiction. However, the killing Hitler paradox is often considered more morally charged because it deals with a real-world historical figure and event, while the grandfather paradox is usually a more abstract concept. Conclusion. The killing Hitler paradox explores the complexity and potential contradictions inherent in time travel, particularly when trying to alter major historical events. It challenges our understanding of causality, free will, and the consequences of intervention in the past. While various solutions exist, such as the Novikov self-consistency principle, many worlds interpretation, and determinism, the paradox remains an intriguing thought experiment that touches on both philosophical and scientific questions about the nature of time, history, and human agency. The future self paradox is a variation of time travel paradoxes that occurs when a time traveler encounters their future self. It involves a situation where an individual from the present travels forward in time and meets a version of themselves from the future, creating a number of potential contradictions and logical issues. The paradox raises interesting questions about identity, causality, and free will. 1. The scenario. The typical future self paradox unfolds as follows. You, as a time traveler, travel forward in time and meet your future self. This future version of you may share experiences, knowledge, and details that could affect your decisions in the present. Depending on the interaction, several possibilities emerge. You might receive advice or guidance from your future self. You might be shown a potential future that could influence your actions. You might even receive information that changes the course of your life, such as a key event or decision that leads to your eventual time travel. This creates a paradox because if you already met your future self, then your future self would have had to live through the timeline where this encounter occurred. But your actions in the present could also be influenced by your meeting with your future self, meaning your future self's timeline could be altered by the information exchanged. Can you really have free will if the knowledge you gain from meeting your future self changes your path? The paradox lies in the feedback loop between the present and the future. 2. Key questions and problems. The future self paradox raises several key philosophical and logical issues. A. Causal loop. One of the main issues is the causal loop or bootstrap paradox that can emerge. For instance, if your future self gives you the information you need to travel to the future, then your future self's existence is predicated on your actions in the present. But if you didn't travel to the future to meet your future self, how would that information be passed on in the first place? This creates a circular cause and effect situation where the future depends on the past and vice versa. Example: you travel forward in time and learn some important information from your future self. You return to the past with that information, which leads you to make different choices that eventually result in you traveling to the future to meet your future self again. However, where did the original knowledge or event originate? It seems to exist without a clear source, as the knowledge was both given to you and learned from your future self, creating a paradox. Identity and continuity. When you meet your future self, you are encountering a version of yourself that has experienced a different timeline, yet you both share the same identity. This raises questions about personal identity. Is your future self really you, or are they a different version of you who has lived a different life? Memory and experience. If your future self remembers events that haven't happened to you yet, is that still part of your identity? How much of your identity is tied to the specific experiences that you have lived through? C. Changing the future. If you encounter your future self and learn something that allows you to alter your future decisions, this could create a feedback loop where your actions in the present change the very future you came from. In this case, the timeline could be continuously shifting based on the influence of the future, leading to potential contradictions. Example: your future self tells you about a tragic event that will happen in the future, and you prevent it in the past. This would change the course of events, possibly preventing you from ever traveling to the future in the first place, thus preventing the interaction from happening. This creates a logical inconsistency. If you alter the future after meeting your future self, how can the future still unfold the same way? 3. Possible resolutions. A. Self-consistency principle, Novikov. The Novikov self-consistency principle could be applied to the future self paradox. According to this principle, if time travel is possible, the universe will prevent any events that would lead to logical contradictions or paradoxes. In the case of meeting your future self, the universe might ensure that no matter what happens during your encounter, the timeline remains self-consistent. For example, if you meet your future self The events that unfold must be consistent with the timeline that leads to your future self's existence. Any change you try to make, such as preventing the future event your future self warned you about, would be prevented, or the timeline would adjust itself to ensure consistency. B. Multiple timelines or parallel universes. Many worlds interpretation. In the many worlds interpretation of quantum mechanics, time travel could create parallel timelines or alternate realities. In this view, when you meet your future self, it doesn't create a paradox because you are encountering a version of yourself from a parallel timeline that diverged after a certain event in the past. For example, when you travel to the future, you might meet a version of yourself from an alternate timeline where you made different decisions. The meeting doesn't affect the timeline you came from because the future you encountered exists in a parallel universe. By changing your decisions based on meeting your future self, you could simply create a new branch of reality rather than altering the timeline you originated from. C. Fixed timeline, block universe theory. Under the block universe theory, or eternalism, time is seen as a four-dimensional block where past, present, and future events all exist simultaneously. This means that your future self and past self coexist in the same block, and time travel would not be able to change the future. In this view, meeting your future self doesn't change the timeline because the timeline is already fixed. You would still encounter your future self, and the events that lead to your meeting with them are already part of the timeline, meaning no paradox occurs because everything is preordained. D. Timeline protection, immutable history. Another possible resolution is that some events in the timeline are immutable. For instance, you may not be able to change key moments in your life, even if you meet your future self. The encounter itself could be part of the original timeline, and even if you try to alter events, history would adapt to ensure the eventual meeting still happens, preventing paradoxes from forming. 4. Conclusion. The future self paradox is a fascinating thought experiment that challenges our understanding of time, identity, and causality. It raises complex questions about whether we can change our future by interacting with a version of ourselves from that future, and whether such interactions would lead to logical inconsistencies or paradoxes. Different theories, such as the Novikov self-consistency principle, many worlds interpretation, and block universe theory, offer possible ways to resolve the paradox and preserve the integrity of the timeline. However, the implications of time travel and meeting one's future self continue to provoke philosophical debates about free will, determinism, and the nature of reality. The parallel universe paradox, often referred to as the many worlds paradox, is a thought experiment in time travel and quantum mechanics that explores the implications of interacting with or altering timelines in a universe where parallel realities or timelines exist. The paradox arises when time travel leads to the creation of multiple branching timelines or universes, potentially causing inconsistencies, contradictions, or unexpected consequences. 1. The many worlds interpretation. The many worlds interpretation, MWI, of quantum mechanics suggests that every possible outcome of an event or decision creates a branching universe. This theory proposes that, rather than a single timeline, there are multiple parallel universes in which different outcomes play out. For example, you make a decision, go left or right. According to MWI, both outcomes exist, but in separate universes. In one universe, you went left, and in the other, you went right. In the context of time travel, the parallel universe paradox arises when actions in the past are taken that branch the timeline, creating multiple versions of reality. If time travelers alter events in the past, they might unintentionally create multiple divergent timelines, leading to potential contradictions and confusion about the original timeline. 2. The paradox. The parallel universe paradox refers to the logical contradictions and potential inconsistencies that occur when actions in one universe lead to the creation of alternative universes. This paradox can take several forms, but some of the most notable ones are: A. Multiple versions of events. If you travel back in time and alter a past event, for example, changing a crucial decision, you may create an alternate timeline or parallel universe where the altered event plays out differently. This leads to the problem of multiple versions of events. For instance, you go back in time to stop a historical event, such as preventing the assassination of a famous leader. In doing so, you create a new timeline where the assassination didn't happen, but you're still living in the original timeline where it did. In the new timeline, you might encounter a world where the consequences of your action drastically change history. Yet, in the original timeline, the world remained unchanged. This creates confusion. Which timeline is the true timeline? Is there any objective reality to which we can refer, or are all timelines equally valid but disconnected? B. Identity and self-interaction. Another aspect of the parallel universe paradox involves interacting with alternate versions of yourself. If you travel back to the past and make a decision that creates an alternate timeline, you may create a situation where you meet a version of yourself from that new timeline. For example, you travel back in time and make a choice that leads to a different future. Now, in the alternate timeline, there's a different version of you who made a different choice in the past. What happens if you interact with this version of yourself? Which version of you is the real you? Are both versions valid, or is one timeline fake or unreal? This raises the issue of personal identity. If there are multiple versions of yourself existing in parallel universes, what defines your true self? And if multiple versions of you coexist, can they influence one another or come into conflict? C. Self-consistency and feedback. Loops. The feedback loop problem arises when a time traveler interacts with an alternate universe that they themselves created. Let's say you travel back in time and make a change that creates a new timeline. Now, in this new timeline, you might discover that you still exist and have memories of your previous timeline. This results in a paradox where your actions in one timeline have affected your existence in another timeline. Example: you create a new parallel timeline by changing an event in the past. In the new timeline, you go on to make different decisions and create a new history, which eventually leads to you traveling back in time again in this new timeline to alter the original event. You might now face a situation where your actions in one timeline appear to be influenced by the consequences of your actions in another, creating a tangled web of timelines and motivations. 3. Potential resolutions. There are several ways to think about or resolve the parallel universe paradox, especially when considering theories like multiple timelines, Novikov self-consistency, and determinism. A. Multiple timelines, branching universes. The many worlds interpretation itself suggests that every choice leads to the creation of a new parallel universe. There is no primary or true timeline. Every possibility is realized in a new branch of reality. In this model, every action taken by a time traveler to alter the past simply creates a new timeline that diverges from the original one, and the original timeline continues without any changes. The paradox is resolved by acknowledging that multiple versions of reality can coexist and that there is no need for one timeline to be privileged over another. Each branch of the timeline is equally real, and no contradictions arise as long as the timelines remain separate. B. Timeline protection, immutable history. An alternative solution, sometimes called timeline protection or history protection, suggests that even if multiple timelines exist, the timeline itself is protected from significant alterations. Under this view, any attempt to change important historical events would be prevented by the universe in order to avoid paradoxes and inconsistencies. This is a variation of the Novikov self-consistency principle, which says that events will always adjust to prevent contradictions. If you travel back in time and attempt to alter a key event, the universe will ensure that things play out in such a way that history remains unchanged, even if you think you're making a change. This ensures that there are no contradictions or paradoxes across timelines. Fixed timeline, block universe theory. In the block universe theory, or eternalism, time is viewed as a four-dimensional block where past, present, and future are fixed. All events in time already exist and cannot be altered. In this view, if you attempt to travel to the past and change something, your actions would be predetermined and already part of the timeline. There are no true parallel universes because history is fixed and no new timelines can form. Time travel would only allow you to experience the past as it already was, and you would never create alternate realities. The paradox is avoided because there is no possibility for diverging timelines. Events are set in stone and cannot be changed. D. Parallel universes with no interaction. In some interpretations, each parallel universe may remain completely independent from the others. If you alter a past event in one timeline, it may lead to the creation of a new universe, but the original universe remains unaffected. The timelines never cross paths, and the different versions of you or the world exist in isolation from each other. This avoids paradoxes by simply treating each universe as a separate reality. 4. Conclusion: the parallel universe paradox poses a complex challenge to our understanding of time travel and the nature of reality. When timelines branch or diverge as a result of time travel, questions arise about identity, causality, and the nature of the timeline itself. Various solutions have been proposed, ranging from many worlds, where each timeline exists independently, to timeline protection, where the timeline prevents contradictions. The resolution often depends on how one views the structure of time, whether as a fixed block, a set of diverging universes, or a self-consistent loop. In any case, the paradox remains a fascinating area of exploration in the realm of both physics and philosophy.